Hi, this is Mrs. Baisden, and this is the aqueous ionic equilibrium calculation review. The next thing we're going to look at are titrations. So we're going to start with strong acid, strong base titrations. So anytime you're doing these problems, if it doesn't say buffer and you're asked to calculate a new pH or you're calculating a volume or molarity, you always want to identify what type of acid and base you're dealing with because the method is different when you're calculating the pH change. So if you have a strong acid and a strong base, and you're asked to calculate a pH change during the titration, you're going to use a BCA table to find moles of H plus and OH minus after the addition. So when you're setting up the BCA table, the equation for strong acid, strong base is going to be H plus OH minus yields H2O. And that's because you're dealing with a strong acid and strong base, which both completely dissociate. Then you're going to convert to molarity by dividing the moles by the new volume. Then you're going to use the concentrations of H plus or OH minus to find the new pH. So we'll look at some examples for that. So this one says I have 25 milliliters of 0.1 molar KOH and it's titrated with 0.1 molar HNO3. What is the pH after 24.90 milliliters of nitric acid has been added? So when I look at this, I would first identify what kind of a titration it is. So KOH is a strong base, HNO3 is a strong acid. So when I set up the BCA table, just like always, has to be in moles. And I'm going to use the H plus from the acid, the OH minus from the base, and that's going to produce water. Okay, so the water is not going to affect the concentration, so I'm going to cross those out. And then I'm going to use the method I used before to figure out moles of each substance in that solution. So I have 0.025 liters of 0.1 mole per liter KOH, which gives me 0.0025 moles of KOH, which is my OH minus. And then I have 0.02490 liters of HCl, which is also 0.1 mole per liter, which gives me 0.00249 moles of H plus. So then those values go into the BCA table. So the H plus was 0.00249, the OH minus 0.0025, and I'm going to subtract the one that is smaller. So I have a smaller amount of H plus, so that's what gets used up. So 0 H plus left, 0.00001 mole of OH minus left. Now before I can calculate a pH, I have to figure out what the actual concentration is, because right now this 0.00001 is moles. So to figure out what I'm going to divide by, I'm going to add my volumes together. So I had 25 milliliters and 24.9 milliliters, which is 0.0499 liters. So that then gives me a concentration of 2 times 10 to the negative 4th OH minus. So then from there, use your pH equations to figure out the pH, which in this case ends up being 10.30. So be careful with the OH minus because you'll have that extra step. So if you take the negative log of the OH minus, don't forget to then subtract it from 14 before your final pH is listed. Okay, the next thing you might be asked to do with the titration is to calculate the volume needed to reach the equivalence point. So when you're doing these types of equations, you're going to use solution stoichiometry. You're going to write out the balance equation to figure out the ratio of acid to base. And when you're setting these up, you always start with the volume of the substance that you have more information about. So here's an example for this one. It says I have 25 milliliter sample of 0.1 molar KOH is titrated with 0.1 molar HNO3. How many milliliters are needed to reach the equivalence point? So I need to know the ratio of acid to base. So I have KOH plus HNO3. So this is going to give me KNO3 plus H2O. And when that's balanced, the ratio of acid to base is going to be 1 to 1. So then when I set up the stoichiometry, I have a volume and a molarity for the KOH, but I only have a molarity of the HNO3. So that means I'm going to start with the volume of the one I know more about, which is the base. So I'm going to go ahead and change this to liters before I put it into my stoichiometry. So 0.025 liters. You can put the milliliter conversion in there if you want, of KOH. I'm going to use the molarity. To get rid of liters. Then I'm going to use my mole ratio from the balanced equation to convert to moles of nitric acid. So 1 mole of HNO3 for every 1 mole of KOH. Then I'm going to use the molarity to cancel out moles. So that's 0.100 moles of HNO3 per 1 liter. And then since it wants milliliters, I'm going to do one more step here to convert to milliliters. Then I would need 25 milliliters of HNO3 to reach the equivalence point. So the other type of calculation you may have to do is it might ask you what is the molarity after the neutralization reaction occurs. It also might be stated as what is the molarity at the equivalence point, what is the molarity after the end point. So lots of different versions of how you might see the wording on this one. So again, on this one, we're going to use solution stoichiometry. We're still going to write the balanced equation to figure out our ratio. We're going to start with the volume of the substance we have more information about, so very similar to what we just did, except this time we're solving for moles of the unknown. Then we're going to divide by the volume to convert it to a molarity. So on this one, I have KOH reacting with HCl, and I want to know what is the molarity of the HCl. So this one's a little different than the other one, but I'm still going to use solution stoichiometry. Still going to start with balance equation. And this one is also 1 to 1. Be careful because they are not all 1 to 1. You always want to write out the equation to check. I'm still going to start with the volume of the one I know more about. And I'm going to go ahead and change it into liters before I put it into the equation here. 0.02070 liters of KOH. 0.5 moles of KOH per 1 liter. According to our balanced equation, 1 mole of HCl per 1 mole of KOH. And then at this point, I can solve for moles. So I have 0.01035 moles of HCl. Then to change that into a molarity, I have to look and see what was the volume of HCl that I started with. So I'm going to divide this by 0.015 liters. So I just converted that milliliters to liters. And that gives me a molarity of 0.69 molar HCl. So very similar, except you stop one step early and then divide by the liters. Okay, now we can also have weak acid, strong base titrations, or weak base, strong acid. So we're going to focus on the weak acid, strong base titrations in our examples here. So if we're doing a weak acid, strong base titration and we want to calculate pH changes, we're going to use a BCA table. The difference is, since this is not strong and strong, we have to use a BCA table and we have to decide which part of the system what you're adding is going to react with. So for a weak acid, strong base equation, you're going to have the weak acid plus the OH minus, which will give you the conjugate base and water. You run it through your BCA table, and then once you have your moles at the end, you convert them back to molarity, then you're going to use the Henderson-Hasselbalch equation to solve for the new pH. So here's an example for that one. I have 40 milliliters of 0.025 benzoic acid, and it gives me a Ka. It's titrated with 0.05 molar sodium hydroxide. So before I start this, I want to make sure I've identified what kind of reaction this is. So benzoic is a weak acid, sodium hydroxide is a strong base. So that's what's going to help me realize that this is going to be a different type of different type of BCA table than the one I'd use for strong and strong. So for this one, I'm going to start with the weak acid. So HC7H5O2. Again, this is BCA. Just as a reminder, everything has to be in moles. And then it's going to react with the OH minus. And then what that's going to generate is the C7H5O2, which is the conjugate base, and H2O. The H2O I'm going to put off to the end here because I'm not going to need that. Just like before, everything has to be converted to moles before it goes into this equation. So the first thing I have to do is figure out how many moles of benzoic acid I have. So for this one, I have 0.040 liters of 0.025 benzoic acid. So that is 0.001 moles of benzoic acid. And then I'm adding 0.010 liters, which is this 10 milliliters, of 0.05 mole per liter NaOH. So that's going to be 5 times 10 to the negative fourth. So that's my initial OH minus. And then for this one, because this is not a buffer, there's no C7H5O2 in there to start with. Okay, then just like my others, I'm going to subtract the one that's smaller from the left, add it to the right, so when I subtract that, I get 5 times 10 to the negative fourth. All of the OH minus gets used up. 5 times 10 to the negative fourth over on this side. Then before I can put it back into the Henderson-Hasselbalch equation, I need to divide by the new the new volume. So before I can put it back into the Henderson-Hasselbalch, I need to divide by the new volume. So I had 0.04 liters and 0.01 liters, which is 0.050 liters. So that gives me 0.01 molar acid, 0.01 molar conjugate base. So now I can use Henderson-Hasselbalch. The pKa for this one will be the negative log of 6.3 times 10 to the negative fifth plus log base over acid. So the pH would be 4.20. So if I'm calculating volume needed to reach the equivalence point for a weak acid, strong base, the method is going to be the same as what it was for a strong acid, strong base. So I'm going to use solution stoichiometry, use my balanced equation, start with the volume of the substance I have more information about. So for this one, I have a 40 milliliter sample of 0.025 benzoic acid, and it's titrated with 0.05 molar NaOH, and I want to know how many milliliters of NaOH are needed to reach the equivalence point. So before I'm going to do anything, I'm going to write out the balanced equation. So I would have sodium benzoate plus H2O. And if I balance this, these are all 1 to 1. So I'm going to start with the one I have more information about, which is the benzoic acid. I'm going to go ahead and change it to liters. I'm I'm going to use my ratio from the balanced equation. So 1 mole of NaOH for every 1 mole of benzoic acid. Then I'm going to use the molarity of the NaOH to convert it to liters, and then convert to milliliters. So this would give me 20 milliliters of NaOH needed. The other type of problem you could do with these is calculating the molarity after a neutralization reaction. So again, this is going to be the same as what we did for strong and strong. So I need the balanced equation, which is going to be the same as, well, actually it's not. So I need the balanced equation, which I have, this time we're using acetic acid, reacting with NaOH. And again, I'm going to start with the one I have more information about. So I'm going to go ahead and convert it to liters, 0.0225 liters of NaOH. Use the molarity to convert to moles. Use the mole ratio, which is going to be 1 to 1. And again, they're not all going to be 1 to 1, so be careful with that. You always want to write out the equation just to make sure. Okay, and then this one we're going to stop at moles, so 0.00225 moles, and then divide by the volume in liters to get the molarity. So for this one I end up with 0.15 molar HC2H3O2. Okay, the last type of calculation that we're going to look at is solubility equilibria. So a couple different things you could be asked to do on this. So for solubility equilibria, which is KSP, you could be asked to solve for the molar solubility or the KSP, or figure out if you're going to have a precipitate form. So we're going to go through an example of each of those. So if you're solving for molar solubility, this is the best way to set these problems up. Start by setting up an ice table, and while looking at your dissociation of whatever your substance is, set up the equilibrium expression, or the KSP. Use the KSP expression to solve for X, because X is equal to the molar solubility in molarity. So if it's asking for molar solubility, basically you're solving for X if you use this method. If you're asked to solve for molar solubility in grams per liter, then you take that value that you found up here and you convert it using your molar mass. If you're asked for a concentration of a given ion, use the ice table to see how the molar solubility, or how your X's, relate to the concentration of the ions. And we'll talk a little bit about that as we go through this first example. So this one says silver chromate, Ag2CrO4, dissolves in water, gives me the KSP. What is the molar solubility of silver chromate in water? Okay, now this you have to be careful of. If it's water, that means you don't have any common ions. If they wanted the molar solubility in some other substance, you would have to pay attention to whether or not that had a common ion. So molar solubility, we're solving for X. Now these are going to be ice tables, so no more BCA tables. These are going to be ice tables, so I'm going to be using molarity when I put them into here. So the first thing I want to do is set up, what does the dissociation look like? So I'm going to get 2 Ag plus and 1 CrO4 minus 2. So that's just dissociating that. Because this is a solid, that first column is not going to change, so we're going to put lines through it. And then, like I said, the next thing I would do is go ahead and set up the KSP expression. So K expression for this is just like all the others, where you raise these to the power of the coefficients. Okay, and then I'm going to set up my ice table. So for this one, because this is in water, there's no common ion, so both those initial numbers are going to be 0. Then I'm going to add the difference using the coefficients. And I'm using x's because I don't know what the molar solubility is. So this is going to be 2x, and this is going to be plus x. This is a 2 because its coefficient is 2. This is a 1x because its coefficient is 1. So that means that equilibrium, I have 2x silver and x chromate. So then over here, I can plug those values that are at equilibrium into this expression. So the Ag was 2x, and then that's raised to the second power. And then CrO4 minus 2 is x. The KSP is given up here, so I'm going to sub that in. So that is equal to 4x squared times x. So 1.12 times 10 to the negative 12 equals 4x to the third. So you're going to divide both sides by 4. So you end up with 2.8 times 10 to the negative 13 equals x to the third. So then when you solve for x is equal to 6.54 times 10 to the negative fifth. And since this is a molar solubility, that is, you have to put a unit on it, so that would be molar. Now, if it was asking for the solubility of an individual ion, you would look at how those ions relate to the x. So if it wanted the solubility of the silver ion, you would multiply this by 2. If it wanted the solubility of the chromate ion, it would be the same as what the molar solubility of the substance is. The next type of solubility problem you could have to do is you could have to solve for KSP given ion concentrations or molar solubility concentration. So you're going to set up your ice table again, set up your expression, use the information given to figure out the concentrations of the ions, and then you substitute those ions into the KSP expression and solve. So this one says calcium fluoride dissolves in water. The molar solubility is 2.15 times 10 to the negative 4. So that is x. So molar solubility, again, we said was x. So calculate the value of the KSP for calcium fluoride. So I'm going to start this one the same way as what I did the other one. So I'm going to set up the dissociation. So Ca plus 2 2F minus. This is an ice table, so these are molarities. Nothing goes in that first column because that's a solid. And then I'm going to set this up the same way with the x's. So this increases by x, this increases by 2x, so this is x, this is 2x. I'm also going to set up the KSP expression. So calcium plus 2, F minus raised to the second power. And then I'm solving for KSP, and they gave me x. So that means that calcium is equal to x. So x for this is going to be 2.15 times 10 to the negative fourth. 2x for this one is going to be 2 times 2.15 times 10 to the negative 4. So those are the values I'm going to sub in for these ions over here. So 2.15 times 10 to the negative fourth. For F, 2 times 2.15 times 10 to the negative fourth. And then don't forget, you have to raise that to the second power. Solve for that. And you end up with 3.98 times 10 to the negative 11. So that would then be your KSP.